Limitations of the cacher implementation. Caching values is a general useful behavior that we might want to use in other parts of our code with different closures. However, there are two problems with the current implementation of cacher that would make reusing it in different contexts difficult. The first problem is that a cacher instance assumes it will always get the same value for the parameter arg to the value method. That is, this test of cacher will fail. So what they're doing here, and what they're, I think I talked about this earlier, but I can reiterate it, is cacher assumes that every a that we pass in, every argument is going to be the same. So if we pass in, let's say 1, right? Cacher is now going to store the value of 1. And now self that value has something. It's a 1. However, if we pass in a new argument, say 2, cache is still going to return the result for when it was calculating based on the argument of 1. That is an issue, and that is the reason why when I first looked at cache, was like, this doesn't seem to be doing what I really, really wanted to do. But in the context of the example that we were using earlier, it worked completely fine. This test creates a new cacher instance. I can just keep showing the test. So we can make it bigger. This test creates a new cacher instance with a closure that returns the value passed into it. We call the value method on the cacher instance with the argument value of 1 and then the argument value of 2. And we expect the call to value with the argument value of 2 to return 2. I didn't expect that, but sure, that's reasonable to expect. Run this test with the cache implementation in listing 13-9 and listing 13-10, and this test will fail on the assert equals with this message. Thread call with different values, panic that assertion failed, left not equal to right, or left equal right, where left was 1 and right was 2. So expected 2, got 1 back. Yeah, we just walked through that verbally. I don't feel the need to write it, but yeah, moving onward. The problem is that the first time we called c.value with 1, the cacher instance saved some 1 in self.value. Therefore, no matter what we passed into the value method, it will always return 1. Try modifying cacher to hold a hash map rather than a single value. The keys of the hash map will be the argument values that we passed in, and the values of the hash map will be the result of calling the closure on that key. Instead of looking at whether self.value directly has a sum or a none value, the value function will look up the argument in a hash map and return the value if it is present. If it is not present, the cacher will call the closure and save the resulting value in a hash map associated with its argument value. Yeah. So in terms of caching, this is lazy evaluation. In terms of memoization, I can never say that word. This is the way you actually go about it. You have a hash map of what your argument was and what the resulting value was. And then as long as the argument that's passed in, as long as the hash map has a value for that argument, then you return that cached value. If it does not have a value for that argument, then that means if a value for that argument does not exist in your hash map, then that means that you have not seen this argument before, that it's a new argument, and that you have to evaluate it. And do they write that for us? They do not. Scrolling down, it doesn't look like they go over that code at all anymore. Do I really want to try to write that off the top of my head? I'm not sure if I can implement that off the top of my head quickly, so I'm going to continue with the book and maybe come back to it. The problem with the current cacher implementation is that it only accepts closures that take one parameter of type U32 and return a U32. We might want to cast the result of closures that take a string slice and return a U-size values. For example, to fix this issue, try introducing more generic parameters to increase the flexibility of cacher functionality. Ooh. So the second problem they're stating is that our cacher implementation is too narrow. Right now, we only want to cache U32 values and take in U32 values as arguments. But given that this is a cacher, maybe in the future we want to take in strings and return a U size, something like that. And in order to expand this functionality, instead of hard coding the types that we want in the function, like the function signature thing, fn U32 return U32, we use more generics and make it expansive to accept other things as well. Capturing the environment with closures. In the workout generator example, we only use closures as inline anonymous functions. However, closures have an additional capability that functions don't have. They can capture their environment and access variables from the scope in which they're defined. Cool. So what they're saying here is that a feature that closures have that functions don't have is that for a closure, let's say it's defined in the scope that's this big, right? The closure is defined here. We have other variables that are outside of the closure scope, but within the same scope as the closure. This closure can reference them within its scope, and they have an example of that. So listing 13-12 has an example of a closure stored in the equal to x variable that uses the x variable from the closure surrounding environment. So we have let x equal 4 here, right? And then we have a closure, which is defined, it takes in a parameter, call it z, and check to see if z is equal to x. Now, if you notice, x is not defined within this closure. X is defined outside of the closure. However, we can still reference it appropriately here. And then to complete the example, we say that y is equal to 4, and then we pass in y to the equal to x, and it checks to see if y is equal to x, which is up here. Here, even though x is not one of the parameters of equal to x, the equal to x closure is allowed to use the x variable that's defined in the same scope that equal to x is defined in. We can do the same thing with functions. If we try the following example, our code won't compile. So here, if you try and do it with a function, same exact thing as you did with the anonymous function, and it won't compile because, well, x doesn't exist in that scope. And the error they say is can't capture dynamic environment in a function item. Use the pipe instead. Pipe, curly bracket, ... closure form instead. So it's explicitly saying you can't do this with a function, try a closure. Okay? The compiler even reminds us that this only works with closures. Right here. Boom. When a closure captures a value from its environment, it uses memory to store the values for use in the closure body. This use of memory is overhead that we don't want to pay in more common cases where we want to execute code that doesn't capture its environment. Because functions are never allowed to capture their environment, defining and using functions will never incur this overhead. Okay? So what they're stating here is that yes, closures capture the environment that it was defined in. However, this is overhead because it has to store this memory, store this information somewhere, and keep it for itself so it can use it. If you do not need this capability, then you should definitely not use closures. You should just use functions because functions do not have this overhead, and as such, I guess the overall performance would be faster if you use a function. Closures can capture values from their environment in 3 ways, which directly map to the 3 ways a function can take a parameter. Taking ownership, borrowing mutably, and borrowing immutably. Okay? These are encoded in the 3 function traits as follows. So the 3, just to reiterate, is taking ownership. Function can do that. You can borrow mutably. You can borrow something and it can be mutable as you can mutate it. And borrowing immutably, as in you're borrowing something and you cannot mutate it. So, function 1 consumes the variable it captures from its enclosing scope, known as the closure's environment. To consume the captured variables, the closure must take ownership of these variables and move them into the closure when it is defined. The once part of the name represents the fact that the closure can't take ownership of the same variables more than once, so it can be called only once. Okay. So what that stated, at least in my mind, is that the environment variables, right? This closure takes ownership of them. And because it takes ownership of them, it can't take ownership of the same variables more than once. It only happens once. Since it only happens once, it can only also be called once. And that's why this is function once. So this is seemingly an anonymous function that manipulates the environment it was called in by taking ownership of variables it needs, and that can only be called once. Okay? Function mutable can change the environment because it mutably borrows values. So for closures that use this function trait, it means that the closure can change the values of the environment. The closure can change the values of the variables that were defined in its same scope because it mutably borrows those values. Understood? And then we have function, which borrows values from the environment immutably. So function borrows values from the environment still, but it is not allowed to change the value of any of those variables that are defined in the same scope as the anonymous function. That sounds like the safest. When you create a closure, Rust infers which trait to use based on how the closure uses the values from the environment. All closures implement function once because they can all be called at least once. Closures that don't move captured variables also implement function mutable. And closures that don't need mutable access to a captured variables also implement function. In listing 13-12, the equal to x closure borrows x immutably, so equal to x has the function trait because the body of the closure only needs to read the value in x. That was a mouthful. Hold on, let's go over that. So all closures implement the function once because all closures has access to their outside environment and they all can be called at least once. Now if you want to restrict things a little bit more, you could do function mutable, which means yes, the closure has access to everything in the environment, but the items in the environment are not being moved to the closure. So here you have a mutable reference that you can manipulate. And then if you want to make things even more stricter, instead of using function mutable, you can just use function, which means you have access to the captured variables, but you cannot manipulate them. So you just have a readable reference. And that should be the borrowing immutably. If you want to force a closure to take ownership of the values it uses in the environment, you can use the move keyword before the parameter list. This technique is mostly useful when passing a closure to a new thread to move the data so it's owned by the new thread. Okay, so if you want to force the closure to take ownership of the values that it's using, then you can use the move keyword, and they have an example of it down here. And they also say this technique is useful when you're moving things from one thread to another, so this new thread has access to it. So like asynchronous programming or thread programming, multi-threaded programs. We'll have more examples of move closures in chapter 16 when we talk about concurrency. For now, here's the code from listing 13-12 with the move keyword added to the closure definition and using vectors instead of integers because integers can be copied rather than moved. Note that this will not compile yet. Alright, so they're giving an example where they're going to use the move keyword, which is going to explicitly make sure that the closure moves things from the scope that it is defined in, if it's using it in its closure body, and moving it to the closure. And they changed the example from using integers to vectors because integers can be copied, right? So they're cheap to copy, and thus you don't need to move them. So they changed it so that we have a need to use the move because vectors are defined in the heap. So here's the example that won't compile yet, and we have our vector. We have the vector equal to x. We have our anonymous function, or closure, and we're using move z is equal to x. Print line can't use x here. You can't use x here because x has been moved. X is now within this code block and can no longer be used here. That makes sense because it's been moved. And then we have y, and we said that we're making sure that y is equal to x. We receive the following error. Error, use of moved value x. And that's because of here. Value moved into closure here. So x is now part of this closure. And you can't use it. Value cannot be used here. Value here. Value used here after being moved. So it can't be used in this print statement. Note, move occurs because x has type and it's a vector, which does not implement the copy trait. So if we're using integers, it's probably still work because integers implement the copy trait, and thus we wouldn't get this error. The x value is moved into the closure when the closure is defined because we added the move keyword. The closure then has ownership of x, and main isn't allowed to use x anymore in the print line statement. Removing print line will fix this example. Most of the time, when specifying one of the function trait bounds, you can start with function, and the compiler will tell you if you need function mutate or function once based on what happens in the closure body. To illustrate situations where closures that can capture their environment are useful as functions parameters, let's move on to our next topic, iterators. Oh, that was dense. That was dense. I think I understand it, but it's gonna need some time for it to sink in for me. I hope that was useful for you guys. If you like the video, subscribe. Outside of that, peace.